data structures and algorithms, we are going to learn today some basic terminology regarding data structures and the notations that we would be following in the rest of this course. We'll begin with just some very simple definitions. An algorithm, which is an outline of the steps that a program has to take, right, or any computational procedure has to take. A program, on the other hand, is an implementation of an algorithm. It could be in any programming language. A data structure is the way we need to organize the data so that it can be used effectively by the program. Yeah. So, you all are familiar with certain data structures, an array or a list, for instance. So, this course is about, you will be seeing a lot more data structures in this course, and you will see how to use them in various algorithms. So, we will take a particular problem, try to solve that problem, and in the process develop data structures, the best way of organizing the data associated with that problem. Okay, so what is an algorithmic problem? An algorithmic problem is essentially that you have a certain specification of an input, as is given here, and you specify what the output should be like. And a specification of an input could be, well, here is one specification: a sorted non-decreasing sequence of natural numbers of non-zero finite length, right? That is an input. That is a completely specified input. I have given two examples here of inputs which meet this specification. I have not given any output specification yet here, right? Now, what is an instance? These are two instances of the input, right? This is the specification for the input, and you can have any possible instance. You can take any sequence of sorted non-decreasing numbers, and that would form an input instance. So, there are infinitely many input instances possible here. So, an algorithm is essentially describing the actions that one should take on the input instance to get an output as is desired, as is specified. And again, just as there can be infinitely many input instances, there can be infinitely many algorithms for solving a certain problem. Yeah, each one of you could do it in a slightly different way. So, that brings us to the notion of a good algorithm, right? If there are so many different algorithms for solving a certain problem, what is a good algorithm, right? So, a good algorithm for us is an efficient algorithm. Yeah, anything that is efficient is good. And what is efficient? Efficient is something which has small running time and takes less memory. These will be the two measures of efficiency that we will be working with, right? There could be other measures of efficiency, but these are the only two we would be considering in this course. And most of our time we would be spending with running time, really. Yeah, space, of course, we will also be analyzing the space, but most of the time would be spent in worrying about the running time of our algorithm. And we would be interested in the efficiency of algorithms as a function of the input size. So, clearly you can imagine that if I have a small input, right, and my algorithm running on that input will take, or my program running on that input will take less amount of time. If the input becomes 10 times larger, then the time taken by the program would also grow. Maybe it becomes 10 times, maybe it becomes 20 times, maybe it becomes 100 times, I do not know, right. So, it is this behavior of the increase in the running time with the increase in the size of the input that would also be of interest to us. Okay. So, we will come to all of these in a short while as we go through these slides. Okay. Now, how does one measure running time, right? So, I said efficiency, running time, very important for us. So, how does one measure the running time of an algorithm? So, one way would be to what I have put down here as an experimental study. You have a certain algorithm, you implement that algorithm, which means you write a program in a certain programming language. You run the program with varying data sets, right. So, some smaller, some larger data sets, some would be of some kind, some would be of a different kind. So, varying composition. And then you clock the time that the program takes, right. And clock does not mean that you sit down with a stopwatch. You would perhaps just use a system utility like, let us say, system current time millis to clock the time that the program takes. And then from that you try and figure out how good your algorithm is. So that's what one would call an experimental study of the algorithm. Okay, now this has certain limitations. So I've put them down. First, you have to implement the algorithm. To be able to determine how good your algorithm is, you have to implement it. Now that's already a huge overhead, right? You have to, a considerable amount of time has to be spent in doing this. Then your experiments can be done only on a limited set of inputs, right? After all, I said the number of instances is infinitely large. You cannot be running, you can only run your experiments on a small set of instances. And that might not really be indicative of the time that your algorithm is taking for other inputs, which you have not considered in your experiments. Further, if you have two algorithms and you have to decide which is better, you have to use exactly the same platforms to do the comparison, right? By platform, I mean both the hardware and the software environments. Yeah, because as you can imagine, different machines would make a difference, not just different machines. In fact, even the users who are working on that system at that particular point would make a difference on the running time of your algorithm, right? So it becomes very messy if you have to do it this way. So what we are going to do as part of this course, and in fact in this very first lecture, is to develop a general methodology which will help us analyze the running time of algorithms. Okay, and we are going to do it as follows. We are going to first develop a high level description of an algorithm, a way of describing an algorithm, and we are going to use this description to figure out the running time and not implement it or any such thing. Our methodology would help us take into account all possible input instances, and it would help us, it will allow us to evaluate the efficiency of the algorithm in a way that is independent of the environment, independent of the platform that we are using. Yeah. Okay, so I said we'll give a high level description of the algorithm, right? This very first point here, we'll give a highlight. So what is this? So this brings me to what we'll call pseudocode, and this is how we are going to be specifying all our algorithms, right, for the purposes of this course. Yeah. So here is an example of a pseudocode, and you might have seen this in your earlier courses also. So what is this algorithm doing? This algorithm takes an array A, which stores n integers in it, and it's trying to find the maximum element in this array, right? What I have written here is not a program, yeah, because I think the syntax is all wrong, yeah, but it is pseudocode. It is a mixture of natural language and some high level programming constructs. So I'm going to be using, so I'm going to come to all of that, but I'm going to be using like a for, do loop, I'm going to use an if then else statement, I'm going to use a while loop, all of that I'll use, right? But I'll not bother about, okay, there should be a semicolon here or there should be a colon here. I'm not going to bother about those. Those are things that are required by a compiler, but for our understanding, this is completely clear what this program is doing, right? So what is this doing? It's keeping track of the maximum in a variable called current max, which is initialized to the first element of the array, yeah, and then it is going to run through the remaining elements of the array, compare them with the current maximum element that we have seen. If the current maximum element that we have is less than the current element, the element under consideration, then it would update current max. AI becomes the new max, yeah, and then when this loop terminates, we would just return current max. So it's a very simple algorithm, but just with this pseudocode you are able to understand what it is doing. This will not run on any computer, it's pseudocode, but it conveys the ideas, it conveys the concepts. Yeah, any questions till this point? Okay, so that's what I was saying, it's more structured, pseudocode is more structured than usual prose, but it's less formal than a programming language. Yeah, and what will our pseudocode look like? We'll use standard numeric and Boolean expressions in it, right? Instead of the assignment operator, which is equal to in Java, I will use this left arrow, yeah, and instead of the equality operator, equality relationship in Java, which is 2 equals, the same in C, I will use just a single equal, yeah, and I'll declare methods in this manner. So name of algorithm name, what are the parameters it takes. I'll use all kinds of programming constructs. So I'll use if then statements, if then else statements, while do, repeat until, for do. To index arrays, I'll say AI, aij, so on and on. Right? It should be clear what this is doing. And I'll use return when the procedure terminates, and return value will tell me what is the value returned by the particular procedure or a function. And when I have to make a call to a method, I'll specify that with method, name of the method, the argument, and what is the object that it is returning. Any questions to this point?
So what was the object?
This is specifying the type of the value returned by the particular method. Yeah, you'll see more of this when we come across more pseudocode. Okay, so how do we analyze algorithms? So we identify what are primitive operations in our pseudocode, right? So what is a primitive operation? It's a low level operation. Examples: data movement. I do an assignment from one to another. I do a control statement, which is a branch if then else, a subroutine call, a return, or I do arithmetic operations or logical operations. These are all, we'll call them primitive operations. And in my pseudocode, I just inspect the pseudocode and count the number of primitive operations that are executed by the algorithm. Yeah. Okay, so we need to take an example now. I'll take an example of sorting. You all know what sorting is. Yeah, the input is some sequence of numbers. Output is a permutation of the sequence, which is in non-decreasing order. Okay? So if this were my input, this should be my output. Okay, what are the requirements of the output? We said it should be in non-decreasing order, and it should be a permutation of the input. Any set of numbers which are in non-decreasing order doesn't make an output, right? Your algorithm should sort the numbers that were given to it, not just produce a sequence of numbers in increasing order. Okay, clearly the running time will depend upon kitne numbers hai, how many elements are there, and quite often it depends upon how sorted these numbers were. If they were already almost sorted, then perhaps your algorithm is not going to take a long time. Of course, it also depends upon what particular algorithm you are using, right? So the running time would depend upon all of these factors. Okay, and the first sorting technique we are going to use is one that you have used very often, right? Let's say when you're playing a game of cards. Okay, so what is the strategy you follow when you are picking up set of cards that have been dealt out to you, right? So you like to keep them in a sorted order in your hand. So you start with your empty hand, you pick up the first card, then you take the next card and you insert it at the appropriate place. So you suppose you have some 5 cards in your hand already, right? Let's say 2, 7, 9, Jack and Queen. Then I get an 8. So I'm going to put it between 7 and 9. That's the right place it has to be in. Yeah. So I am inserting it at the appropriate place, and that's why this technique is called insertion sort. And I keep doing this till I have picked up all the cards and inserted them appropriately in the hand that I have. Okay, great. So what's the idea? So this is the pseudocode for insertion sort, and we'll just run through this so that you all understand. I give you as input an array of integers, let's say A contains the input. The output is a permutation of the original numbers such that it is sorted. So my output is also going to be in the same array. This is the input output specification. Okay, I'm going to have 2 variables or 2 indices I and j. Yeah. Okay, the array is going to be sorted from A1 through AI. At any point in time, it's going to be, sorry, A1 through AJ minus 1 is going to be sorted. J, the jth location, is the element which I have to insert appropriately at the right place. Yeah. So clearly J then has to vary from 2 to n. Is that right? So J has to vary from 2 to n. So I'm going to look at the jth element. I put that in key. And now this is what I have to do. I have to insert AJ, or I have to insert the key into the sorted sequence, which is A1 through AJ minus 1. A1 through AJ minus 1 is the sorted sequence. And I am going to use the index I to help me do this. Yes? What is index I going to do? Index I is going to run down from J minus 1 down to 1. Yeah, we are going to decrease index I, which is what we are doing here in this while do loop. It starts with the value, J minus 1. And what am I going to do? Let's see, what am I going to do here? I have to insert 7. I am going to move this 9 to this location. Yeah. Why? Because 9 is more than 7. So 9 is more than 7, I move it here. Then I compare 7 with 8. 8 is still more than 7, so I'll move it right. Then I compare 7 with 6. 6 is smaller than 7. So now I have found the right place for 7, and I would put 7 in here. That's exactly what is happening in here. I run through this loop till I find an element which is less than key. Key is the element I am trying to insert. So this loop will continue while the element I am considering is more than key. This loop will terminate when I see an element which is less than key, or the loop will terminate when I reach I equals 0. In which case, that means that I have moved everything to the right and I should insert the element at the very first place. And what am I doing here? I am just shifting the element one step to the right. Yeah. So note that I have to insert this at the right place. So I shift 9 right one step. Now this location becomes empty, so to say. Then I shift 8 one step. So this location now becomes empty, and now I can come and put 7 in here, which is what I do eventually. So I plus 1 would be the index where this location, which would be the empty location eventually, and I put in key there. Okay. So it's a very, you can all implement it. Maybe you would have implemented it in a slightly different way. That would give you a different program, right? But the algorithm is essentially the same. You are going to find the right place for the element and insert it there. Okay. And now let's try and analyze this algorithm. Okay. So I've put down the algorithm here on the left. There is a small mistake here. This should be a left arrow. Please make a correction of that. Okay. What we are going to do is, let's count. So these are all my primitive operations, right? This is a primitive operation. This is a primitive operation. Here I have two primitive operations really. Why? Because I am comparing I with 0, and I am comparing AI with key, and actually I am also taking an AND. So there are 3 primitive operations. Yeah. So there are a certain number of primitive operations here. This is also primitive. So all of these are primitive operations. And what I am doing here, so each of these operations take a certain amount of time depending upon the computer system you have, right? So C1, C2, C3, C4, C5, C6 just reflect or just represent the amount of time that these operations take. In whatever units, I don't care. Yeah. And here I am counting the number of times each of these operations is executed, is done in this entire program. Now, why is this operation done n times? It says n times. So I start by assigning j equals 2, then assign 3, 4, 5, 6, 7, I go all the way up to n, and then when I increment it maybe once and I check that, oh no, it's now more. So I have counted it as n times, right? So there might be small errors in n and n plus 1, that's not very important. So this is roughly n times that we have to do this operation. How about this operation? I'm going to do it exactly n minus 1 times. Once for 2, once for 3, once for 4, up to n. Right? So that's why I have that this operation is being done n minus 1 times. Right? Let's forget this. This is just a comment statement. Again, this operation will be done exactly n minus 1 times. Right? Now we have to look at how many times this particular, how many times do I come to this statement? Right? Okay. T sub j reflects the counts the number of times I have to shift an element to the right when I am inserting the jth card into my hand. Okay. So in the previous example, when I am inserting 7, I had to shift 2 elements, 8 and 9. Yeah. So T sub j is going to be counting that quantity. Okay. And that is the number of times I am going to reach this part of my while loop. Yeah, I am going to be checking this condition. So first I come to this condition, then maybe I come again to this condition, I come again over and over again to this condition. So I am going to, for one iteration of this for loop, or in the jth iteration of this for loop, I am going to reach this condition T sub j times. And so the total number of times I am seeing this condition is the sum of T sub j as j goes from 2 to n. Okay. So every time I see this condition, I also come here, right? I'm going to be seeing this condition, I'm going to come to this statement one more time than I come here, because the last time I see this statement, I would exit out of here. So that's why this is Tj minus 1, and similarly for that same reason, this is Tj minus 1, j going from 2 to n. Okay. And this statement here is not part of this while loop. Okay, this is an assignment operation, please correct this. This is not part of the while loop, and so this statement is part of the for loop, and it is done exactly n minus 1 times as are the other statements. Right? And so the total time that this procedure takes, if you knew what these constants were, can be computed in this manner. Of course, you do not know what T sub j is. Right? T sub j is a quantity which depends upon your instance, not problem. Right? There is a difference here. Problem is one of sorting. The instance is the set of numbers, the sequence of numbers that is given to you. So T sub j depends upon the instance. And let's see what difference T sub j makes. So if the input was already sorted, T sub j is always 1. I just have to compare the element with the last element, and I will immediately see that it is larger than the last element, and so I would not have to do anything at all. So T sub j is always a 1 if the input is already in increasing order. What happens when the input is in decreasing order? Yeah, if the input is in decreasing order, then the number that I am trying to insert is going to be smaller than all the numbers that I already have. Yeah, because the input is in decreasing order. The number I am trying to insert is smaller than the numbers that I already have sorted in my array. So what am I going to do? I am going to compare it with the first element, the second element, the third element, the fourth element, all the way up to the very first element. Right? So when I am trying to insert the jth element, I am actually going to end up comparing it with all the other j elements in the array. And so in that case, T sub j will be equal to j. And when T sub j equals j, note what this quantity becomes. It's summation j going from 2 to n. You all know it's of the kind n squared. Right? And in that case, the running time of this algorithm would be some constant times n squared plus some other constant times n minus some other constant. Right? The behavior of this running time is more like n squared. We come to this point later when we are talking of asymptotic analysis, but this is what I mean by f of n squared. It will behave more like n squared. Here, on the other hand, in the best case when Tj was 1, this sum here is just n or n minus 1. And in that case, the total time is n times some constant plus n minus 1 times some constant minus some constant, which is roughly n times some constant, right? Sorry. And so it's what we call a linear time algorithm. I come to these things again. On an average, okay, now on an average, what would you expect? In the best case, it is something like that you have to compare only against one element. In the worst case, you have to compare about with j elements. In the average case, you would expect that you would compare against half of those elements, right? So in an average case, if you were to take it as you are comparing against j by 2, even then this quantity, summation of j by 2, j going from 2 to n, what will this be? This will be roughly n squared by 4 now. Yes? And so its behavior is again like n squared, and we come to these points in a minute. Okay, so this is what I mean by best, worst and average case. So I take the size of the input, suppose I am interested in sorting n numbers, and I look at all possible instances of these n numbers, yeah, infinitely many. So again, it's not clear how exactly one would do that. So what is worst case defined as? Worst case is defined as the maximum possible time that your algorithm would take for any instance of that size. So these are all instances of the same size. Yes? The best case would be the smallest time that your algorithm would take. And the average would be the average of all of these infinitely many bars. Yes? So that was for inputs of one size n. That would give us the values of, we can then therefore compute worst case, best case and average case, right? Now if I were to consider inputs of all sizes, I can then create a plot of this kind. For each input size, I can figure out, suppose I could figure out what the worst case, best case and average case were, then I would get such monotonically increasing plots. Yeah. Why is that? It's clear that as the size of the input increases, the size of the time taken with your algorithm will increase. It's not going to happen that your input size becomes larger and it takes lesser time. So which of these is of interest to us, or which of this is easiest to work with? Worst case is the one that we will use most often, and for the purposes of this course, that's the only measure we will be working with. Why is that? First, it provides an upper bound. It tells you how long your algorithm is going to take in the worst case. Many algorithms, it occurs fairly often. Quite often, it is the case that your worst case, that for many instances, the time taken by the algorithm is close to the worst case, right? So that average case essentially becomes as bad as the worst case, right? In fact, for the previous example that we saw, average case was like n squared and worst case was also like n squared. Of course, there were a difference in the constants, but it was roughly the same. Now, average case might be a very difficult quantity to compute, because I said average case, if you have to compute, you have to look at all possible instances and then take some kind of an average, right? Or you have to say, okay, my input instances are drawn from a certain distribution, and so the expected time my algorithm will take if an input instance is drawn from this distribution is going to be so much. So it's typically a much harder quantity to work with and compute. So worst case is the measure of interest, is what we will be working with. Okay, so asymptotic analysis is the kind of a thing that we've been doing so far when I said n squared and n. And the goal of this is really to analyze the running time while getting rid of superficial details, right? We would like to say that an algorithm which has a running time of some constant times n square is the same as an algorithm which has a running time of some other constant times n square. Why? Because this constant is typically something which would be dependent upon the hardware that you are using. right? In the example that I showed you, the C1, C2, C3, all of those times would depend upon the computer system that you're using, the hardware, the compiler, many factors, right? And so we would not like to distinguish, or we are not interested, or we are not bothered about distinguishing between such algorithms. Both of these algorithms, one which has a running time of 3n square perhaps, or another with the running time of n square, have a quadratic behavior, as in when the input size doubles, both of the algorithm, their running time increases fourfold. Yeah, and that is the thing that is of interest to us. So we are interested in capturing how the running time of the algorithm increases with the size of the input in the limit. Yeah, this is the crucial point here, and that's what asymptotic analysis is all about. That's what the asymptotic here is. In the limit, how does the running time of this algorithm increase with increase in input size? Okay, that brings us to something that some of you might have seen before, the big O notation. So if I have functions f of n and g of n, f of n and g of n, n here is typically representing the input size. F of n is measuring the time that your algorithm is taking. So f of n and g of n are both non-negative functions. Not just non-negative, they are also non-decreasing, right? Because as input sizes increases, the value of the running time, the time taken by your algorithm, would also increase. Yeah, so these are both non-decreasing functions of n, and we say that f of n is big O of g of n if there exists constants c and n naught, such that f of n is less than c times g of n for n larger than n naught. So what does all of this mean? So I have drawn two functions here. The function in red is f of n, and g of n is some other function. This function in green is some constant times g of n. Now as you can see, beyond this point n naught, c times g of n is always larger than f of n. So I have not, suppose this is the way it continues even beyond this point. Yeah, then we would say that f of n is big O of g of n, or f of n is order g of n. Okay, so a few examples would clarify this, and we come to that. Okay, my function f of n here is 2n plus 6, okay, and g of n is n. Right? It is the case, so if you look at these two functions, 2n plus 6 is always larger than n. Yes, so which is why this function 2n plus 6 is always above n. Now you might be wondering why 2n plus 6 is a nonlinear function here. That's because the scale here is an exponential scale. Yeah, so it's 2 to the 0, 2 to the 1, 2 to the 2, and so on, and so on, and similarly on this axis. Yeah, so this is n, and this blue line here is 2n, and this is 4n. Okay. Now as you can see, beyond this point, f of n is less than 4 times n. So what are our constants c and n naught? The constant c is 4, and n naught would be this point of crossing, beyond which 4n becomes larger than 2n plus 6. Right? What is this point of crossing? At what point does 4n become larger than 2n plus 6? 3. Right? So your n naught becomes 3 here. Right? And then we say that f of n, which is 2n plus 6, is big O of g of n. Not big O of 4n, but big O of n. Right? So f of n here is big O of n then. So 2n plus 6 is big O of n. Another example. The function in red is g of n, which is n, and any constant times g of n, so it's the same scale as in the previous slide, any constant time g of n will just be the same straight line displaced by suitable amount, right. So this will be 4, this will be 4 times n, this will be whatever, depending upon what the intercept here is, right. So it will just be like this, but your n squared would be a line like this, okay. So there is no constant c such that n square is less than c of n. Can you find out a constant c such that n square is less than c n for n more than n naught? No. Any constant that you choose, I can pick a larger n. I can pick an n such that this is violated. And so it is not the case that n square is big O of n. Yeah. So how does one figure out these things? So there is a very simple rule. Suppose this is my function 50n log n. I just drop all constants and lower order terms. So forget the constant 50 here and I get n log n. So this is big O of n log n. This function 50n log n is big O of n log n. Yeah, 7n minus 3 is, I drop the constants and lower order terms, I get 7n minus 3 is big O of n. I have some complicated function like 8n square log n plus 5n square plus n. I just drop all lower order terms. So this is the fastest growing term because this has n square as well as log n in it. So I just drop the n square and n term, and from here I drop my constant and I get n square log n, right. So this function is big O of n square log n. There is a constant c such that this quantity, this large sum here, is less than c times n square log n for n larger than some n naught. So in the limit, this quantity will be less than some constant times this quantity, right. And you can figure out what the value of c should be and what the value of n naught should be for that to happen. Okay. Now this is a common error. So this function 50n log n is also big O of n to the 5. Yes or no? Yes. Why? Because, well, this quantity in fact is less than or equal to 50 times n to the 5 always for all n. Yes, and that is just a constant. So this is big O of n to the 5. Right? But when we use the big O notation, we try and provide as strong a bound as possible. Right? So instead of saying while this statement is true, we will rather call this as big O of n log n. Right? You will see more of this in subsequent slides. Okay, so how are we going to use the big O notation? So we are going to express the number of primitive operations that are executed during a run of the program as a function of the input size, and we are going to use the big O notation for that. Right? Now if I have an algorithm which takes, for which the number of primitive operations is big O of n, and some other algorithm for which the number of primitive operations is big O of n square, then clearly the first algorithm is better than the second. Why? Because as the input size grows, you know, if the input size doubles, then the running time of this algorithm is only going to double, while the running time of this algorithm will increase fourfold. Right? Similarly, our algorithm which has a running time of big O of log n is better than one which has a running time of big O of n. And we have a hierarchy of functions of this kind, log n, n square, and an algorithm with a running time of big O of log n is better than one with a big O of n, with better than one with a big O of running time of big O of n squared, a running time of big O of n cube, which is better than an algorithm with a running time of big O of 2 to the n. So there is a word of caution here though, right? So you might have an algorithm whose running time is 1,000,000 times n, right? Because you are doing a whole lot of maybe some other operations. I can't see how you would create such an algorithm, but you might have an algorithm of this running time, right? So this is big O of n, right? Because this is less than or equal to some constant times n. And you might have some other algorithm with a running time of 2n squared, right? So from what I have said before, you would say that this algorithm is better than this. Yeah, the one with the linear running time of big O of n running time is better than this. It is true, but in the limit, and the limit here is achieved very late when n is really large. For small instances, you know, this 2n square might actually take less time than your 1 million times n, right? So you have to be careful about the constants also. Okay, so we'll do some examples of asymptotic analysis. So I have a pseudocode written here, and what I'm doing here is I have an array of numbers, n numbers sitting in an array called x, and I have to output an array A in which each element, in which the element AI is the average of the numbers x0 through xi. Okay, this is what I have to do. Okay. So what is one way of doing it? So I compute, so I basically have a for loop in which I compute each element of the array A, right? So to compute A10, what should I do? I just have to sum up x0 through x10, which I am doing here, right? So what is this doing? To compute A10, so when I am computing A10, I is taking the value 10, and I am running the index j from 0 to 10. I am summing up the value of x, x0 plus x1 up to x10 in this accumulator A, and then I am eventually dividing the value of this accumulator with 11, right, because it's x0 through x10, and that gives me the number that I should have in A10. Yeah, and I'm going to repeat this for 11, 12, 13, 14, all the elements essentially of it to get. Is this a good algorithm? It's not a good algorithm? It is an algorithm, right? And let's compute what its running time would be like. Okay, this is one step. How many times is this step executed? It's executed I times. And what are the values that I takes? Initially, I takes a value 0, 1, 2, 3, all the way up to n minus 1, right? And this entire thing is done n times, right? So what does that give you? That gives you a total running time of roughly n square. This one step is getting executed n square times, and this is the dominant thing, right? Of course, this will, how many times is this step getting executed? This step is getting executed n times, and so is this step, which is getting executed n times. But this step is getting executed roughly n squared times, some constant times n squared times, and so running time of your algorithm is big O of n squared, right? It's a very simple problem, but you can have a better solution here, right? And perhaps all of you can see what the better solution should be. What's the better solution? We will have a variable s in which we would keep accumulating the xi's, right? So initially s is just 0, and then when I'm computing AI, I already have in s, before that point I already have in s x0 through xi minus 1, right, because I used that at the last step. That's the problem that is happening here. See, every time we are computing x, so first we are computing x0 plus x1, then we are computing x0 plus x1 plus x2, then we are computing x0 plus x1 plus x2 plus x3. We're kind of repeating computations over and over again. Why should we do that? Right? We'll have just the single variable which will keep track of the prefixes, the sum of the prefixes so far, right? So s at this point, when I am in the ith run of this loop, s at that point already has the sum x0 through xi minus 1, and then I sum xi in it, and to compute the ith element I just need to divide this sum by I plus 1, right? And I keep this accumulator around with me. Now when I finish the ith run, ith iteration of this loop, I have in s x0 through xi, x0 through xi, the sum x0 through xi, right? I can reuse it for the next step. So how much time does this take now? In each run of this loop, I am just doing 2 steps, 2 primitive operations, right? So that makes it order n time. right, because this loop is executed n times. Okay, so I've been using this freely, linear and quadratic, but here's a slide which just tells you the other terms that I might be using. So linear, if an algorithm has a running time, an asymptotic running time of order n, then we call it a linear algorithm. If it has an asymptotic running time which is n squared, we call it quadratic. Logarithmic if it is log n. Polynomial if it has n to the k for some constant k is a constant here. And an algorithm is called exponential if it has a running time of a to the n, where a is some number more than 1. Yeah. So till now I have only introduced to you the big O notation. We also have the big omega notation and the big theta notation. The big omega notation provides a lower bound, right? A function f of n is omega of g of n. So this is f of n, this is g of constant times g of n. If constant times g of n is always less than f of n. Earlier this was more than f of n. Less than f of n in the limit. So beyond a certain n naught, right, as this picture illustrates. So f of n is more than c times g of n beyond this point n naught. Okay, and in that case we will say that f of n is omega of g of n. The theta notation, f of n is theta of g of n if there exists constant c1 and c2 such that f of n is sandwiched between c1 times g of n and c2 times g of n. That is, beyond a certain point, f of n lies between one constant times g of n and another constant times g of n. So then we say that f of n is theta of g of n. That is, f of n grows like g of n in the limit. Okay. Another way of thinking of it is f of n is theta of g of n if f of n is big O of g of n and it is also omega of g of n. Right. This part tells you that f of n is big O of g of n, and this part tells you that f of n is omega of g of n. Right. And so we have that f of n is theta of g of n. There are two more related asymptotic notations. One is called the little o notation and the other is called the little omega notation. They are the non-tight analogues of big O and they are the non-tight analogues of big O and big omega, and it is best to understand this through the analogy with real numbers. So when I say that f of n is big O of g of n, I am really saying that the function f is in some sense less than or equal to g, right. That is in fact what we used in the definition. F of n is less than c times g of n. So f is kind of, so the analogy with real numbers is when a number is less than or equal to another number. Omega is for greater than or equal to, theta is equal to. Of course, these are functions, well these are real numbers. So if these are real numbers, you can talk of equality, but you can't talk of equality of functions unless they are exactly equal. So this is the corresponding notion for that. Little o now corresponds to strictly less, okay, and little omega corresponds to strictly more. So we are not going to be using these. In fact, we will be spending most of our time with just big O. Okay, so that's a part you should be very clear with.
But what do they specifically mean that it is strictly?
Okay, for that I'll just maybe look at the slide. So the formal definition for little o is that for every constant c, there should exist some n naught such that f of n is less than c times g of n for n more than n naught. How is it different from big O? There it said there exists a c and an n naught such that this is true. Here we want to say for every c there should exist an n naught for which this is true. Okay, great. So this is just one slide that I put up to show what the difference between these functions is like. So suppose I have algorithms whose running times are like 400n, 20n log n, 2n square, n to the 4 and 2 to the n. Yeah, and here I list out what is the largest problem size you can solve in 1 second, 1 minute and 1 hour. Okay, so the largest problem size you can solve is roughly 2500. Say this is using some constant, so it's, let's say 2500. If you had this as your running time, let's say so this is what the problem size would be like. Okay, why do you see that this is larger than this, although this is a worse running time than this in big O? Because of the constants. Yeah, so you see the difference happening here. If it is 2n squared, then it's already only a problem of size 707 that you can solve. If it's 2 to the n, you can only solve a problem of size 19. And see how the behavior is as the time increases, right? An hour is 3600 seconds, and so you see a huge increase in the size of the problem you can solve if it were a linear time algorithm. Still a large increase when it's an n log n algorithm, not so large an increase when it's an n square algorithm, and almost no increase when it's a 2 to the n algorithm. Right? If you have an algorithm which has a running time of something like 2 to the n, you cannot solve a problem of more than size 100. Cannot solve means it will take millions of years for you to do that. Right? So that is the behavior that bothers us. That's the behavior we are interested in this course. That's why asymptotic analysis is what we will be considering most often. Okay? So any questions till this point? So with that, we are going to stop this lecture. So today we have looked at asymptotic analysis and some initial notation and terminology that we will be following with this course. Okay.